So today we're going to go back to some inverse trig functions and figure out how to take the derivative of these puppies. Most of this is pre-calc and a bunch of formulas. And honestly, this is not crucial information, but it's one of those things where if we didn't talk about it, you'd get 2 or 3 questions on the AP test. Now that we're going to talk about it, you'll probably never see a question like it on the AP test. We call that Murphy's Law.
Right, so if we just stop now.
Can't go off, you will.
What's that?
If we just stop now, would that be like big?
You think you're going to trick the AP, the College Board? I'll show you guys.
We learn everything.
Yeah, exactly. All 5s. Okay, so we're going to talk about the trig functions again. We're going to learn how to differentiate those, take the derivative of those puppies. And we're going to kind of wrap everything up into one nice little package today. That this marks the end of our derivative studies. So you'll see at the end, I've got some charts for you that'll make you feel all warm and fuzzy inside.
Is it about our memories together?
Sorry, what?
Is it just our memories together?
Yes. It'll be nice. Got a little slideshow for you all the time. All the Trig Tuesdays. And I'm going to get a little truck down. And then, of course, for today, you should be able to name all the presidents in order of descending heights. Well, we know who the first one would be, right? Abraham Lincoln. Abraham Lincoln. Any idea who the second one is?
George
Washington. I actually think it might be Bill Clinton. He was surprisingly tall.
He was a musician.
Who's the shortest?
Yeah. I don't know. I want nothing to do with that. For the record, this is Mike Reedy talking. I had nothing to do with that last wheelchair comment. There, now I'm covered in a court of law.
Was that Paul?
No, it wasn't.
Yeah, you know me.
Okay, so let's talk about, I don't know, the sine function. Okay. Visualize in your mind what the sine graph looks like. Why does it not have an inverse?
Let's talk about donuts.
Hey everybody, it's Mr. Beloff.
When are you bringing the donuts?
Yeah, where are the donuts? It's
Bella,
Trig
how'd that pie
Tuesday.
taste?
She's eating your pie?
Who uses shaving cream for pies?
Yeah, that's horrible. I'm not participating next year unless they get whipped cream.
You should have whipped out a razor and started shaving.
I did not.
Yeah.
Hey, Barbara, made it American. Hold still. Question here in the front.
James Madison was 5'4".
Oh.
What'd you say?
James Madison was what?
So let me explain something to you. You know, I start every lesson with a list of things they should be able to do, and then usually the last one is kind of something quirky or, so that was today's. And so we were talking about who the tallest was, and then somebody asked who was the shortest, and somebody who will remain unnamed goes, Franklin Roosevelt, because he was in a wheelchair.
Short. I agree. Robin's crying over there.
Who was the second tallest?
I think I just was the second shortest.
Oh, Johnson. Is Clinton up there? 6'2", right? So, inverse functions. Visualize in your mind what the sine graph looks like. Why would that sine graph not have an inverse function?
It doesn't pass the horizontal line test.
Atta boy!
You're just trying to redeem yourself after that? Perfect. It doesn't pass the horizontal line test. It's not 1-to-1. When you reflect it over the line, y equals all that other stuff. But mainly, it doesn't pass the horizontal line test. We still want to be able to talk about inverse trig functions, and I'm almost sure you did this in pre-calc, but what we do then is say, okay, we're not going to look at the entire sine graph. We're not going to look at the entire secant graph or cosecant or all the other of the 6 trig functions. We're going to restrict the domain. So we're just going to chop a chunk out of the graph so that it passes the horizontal line test. And you can do that a whole bunch of different ways. If you imagine again in your mind what the sine graph looks like, you can chop out any part of that sine graph as long as it still passes the horizontal line test. You probably want to go from maybe peak to valley, or from valley to peak, or from whatever it takes so that it passes the horizontal line test. Okay. And those are our restrictions. Okay. By the way, IFF, do you know what that stands for? Thank you. I'm so proud. If and only if. So you'll notice sine is restricted in quadrants 1 and 4. Why quadrants 1 and 4? Because in quadrant 1 it's going to be positive, in quadrant 4 it's going to be negative. So we have that covered. Now, why didn't they do 1 and 3? I have no idea. Why didn't they do 2 and 3? I have no idea. I don't know why these particular quadrants were picked, other than we're covering the full gambit of positive values and negative values. Now, how are you going to remember that? If you look, sine corresponds to cosecant. They have the same quadrant restrictions. Cosine corresponds to secant. They have the same quadrant restriction. It would seem logical that tangent and cotangent would have the same quadrant restrictions, but they don't. Why? I don't know. Tangent is in 1 and 4. Cotangent is 1 and 2. It's one of those sweet mysteries of life. That's exactly correct. It's because they don't like you. Way back when, Isaac Newton was thinking to himself, let's screw over this Paul guy. Somewhere in the future, some smart aleck named Paul is going to show up and this will stick it to him. Okay, so, what are those values? Okay, so what am I asking here? If we look at part A, I'm looking for where on the unit circle does the sine have a value of -1/2? Without the domain restrictions, we would have an infinite number of answers. Yes? You remember that, right? Find out where it is, but then you can keep going around, and they all have 2 answers because, you know, you go across for y's, down for x's, 180 degrees for tangents, all that other fun stuff. But now we have a domain restriction. And again, what's the domain restriction on sine? Well, we want to restrict sine to a positive quadrant and a negative quadrant. And since sine relates to the y value, we would be in quadrants 1 and 4. Where in well, first of all, what quadrant will that be in? 1 or 4? 4, because it's negative. Where is the sine equal to 1/2 in the 4th quadrant? Say again?
-5/6.
Outstanding. Now, some of you may have said to yourself, it's not -π/6, it's 11π/6. They're the same location. Why is -π/6 the correct answer? Because now we're going from 0 and going up for positive, down for negative. Get all this weird persnickety stuff that shows up. Would it be the end of the world if you said 11π/6? Probably not, except that's outside the domain restriction. 11π/6 is all the way around. Okay, so where's the cosine equal to 0?
Wait.
Or negative pi. Why pi/2 and not -π/2? Well, let's go back to the domain restriction. This one is really picky. Whoops. And you'll see that we are including some and not including the others for the cosine. Yes, sir.
Is this the same thing that we learned last year? It's like all students calculate. So it's like all in the first quadrant, sine is in the second. Is that totally different?
No, that's the same thing. Yeah, I don't teach it that way, so that's still kind of. Yeah, have you heard that before? All students take calculus. So yeah, it helps you remember what. See, I do it differently. I know that sine always relates to y, so I use it that way to figure out where it is. Cosine relates to x, so that helps me with quadrants, and then tangent is sine over cosine. Okay. Tangent can sometimes be tricky because we have a fraction going on there. That fraction, and I don't know if this helps you or hinders you, is the same thing as the square root of 3 over 2 over 1/2. Because the square root of 3 over 2 and 1/2 are prominent values in a unit circle, that might help you figure that out. Okay, remember that tangent is sine or cosine. That's y over x. So where's the y value equal to the square root of 3 over 2? Where's the x value equal to 1/2? And that happens at pi over 3. This will come flooding back to you as we continue. Is 0.3 on the unit circle? No, then you pick up your handy dandy calculators. You make sure you're in radians mode. That was a hint. Yeah, there you go. I don't know why you wouldn't be in radians mode, but just check to be sure. Arc sine, the same thing as the inverse sine, which is above the sine button of 0.3. Tells me that you get a value of how much? What's that? Okay.
0.30469.
Attaboy, Ben. There you go. 0.30. Okay, just for giggles, take the arc sine of 1.6, please. What happened? Error. Ooh, why? You just waving your pencil in the air like you just don't care. Don't hurt yourself. Come on, you got this. Why doesn't the arc sine of 1.6 work? Again, think about the graph of the sine function. Gosh.
If it's outside, it's still base.
Correct. Would it? Well, technically that's the range.
Oh.
In French, it would be the range. What's the range of the sine?
Negative pi over 2 is pi over 2.
Yeah, 1 to -1. If you again envision what the sine graph looks like, the sine graph never gets any taller than 1 and never gets any smaller than -1. So your y values that it puts out must be between 1 and -1. Therefore, when you try to find what x value generates that y value, you get an error. So let's try something different here. How about the tangent of 1.6? Sorry, my bad. Arctangent of 1.6. So that one we got a value on. Why? Anybody? Me y, you y, him y, z, she y, u z. What's tangent graph look like? Yeah, it goes up, goes all the way down and all the way up to infinity. So we can get any value from that. Do you recall what the secant and the cosecant graph looks like? Sine but flipped. Be more specific.
Yeah.
For those of you that haven't done this in a while, a visual little graph here might help. So if you're doing a secant graph, a secant graph is based off of a cosine graph, so I would do a cosine graph.
Oh, right.
Then wherever it crosses the x-axis generates asymptotes. And then you've got a down U and an up U. So this, I should have changed colors. This and this represent the secant graph. Okay. So notice the secant graph is the opposite of the cosine graph. So the cosine graph, we have to get values between -1 and 1. The secant graph can't have values between -1 and 1. It's got to be bigger than 1 and less than -1. Okay, we good? Still pre-calc stuff, yes? Bien. Gracias. This is the thing that comes up, blah, 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 but read the stuff in red. There's an automatic assumption that if you take the arc sine of the sine of a function, they just cancel each other. That doesn't always work. It works just fine if you're in the domain of the inverse function, but once you step out, you're going to get a different answer. So my opinion is the best bet is just to do it. So what's the sine of 3 pi over 4? The sine of 3 pi over 4 is 1 over the square root of 2. What's the arc sine of 1 over the square root of 2? We're no longer in the second quadrant. We now pop back to the first quadrant. And that's why you get pi over 4 and not 3 pi over 4. Sometimes they will cancel. You know, if I do the arc sine of the sine of pi over 4, then I get pi over 4 because I'm in the first quadrant. So, for instance, just 1/2. Easy peasy. 1/2 is in the first quadrant. First quadrant, no problem, we're good to go. Cosine, negative pi over 4, is that in the domain of the cosine? Cosine is 1 and 2, so the answer is no, because that's in quadrant 4, so you got to do it the hard way, which gives you that. The unit circle is going to start coming back to you very quickly. If you already don't have it burned into your psyche, this will help. But you do need to know that puppy inside out, forward, backwards. Uh-oh! As my grandfather would say,
This ain't cheap.
2 turds is not on the unit circle. How do I do this? One possibility is a calculator. Oh, wait, it's on the non-calculator portion of the exam. What will you do? What will you do? One option is to cheat, correct. Cry is another option. Pray, thank you. Anybody else?
Skip it.
Skip it.
Neighbor's paper?
Yes.
Neighbor's paper, cheating, yes.
Hey.
Bribe the guy you
Jump out the window.
bribe the guy.
All the fire alarm.
Go to the bathroom.
There you go. Or, I'm gonna get kind of crazy here, or we could just draw a triangle.
No.
Yeah, I know. When in doubt, draw a triangle.
You're being serious.
So I decided to call that angle theta, because I'm pretty good with the Greek letters. And that's a cotangent. And from my vast stores of math knowledge, I know that cotangent is adjacent over opposite, because it's the reciprocal of the tangent. So I got that pretty little triangle. It doesn't matter which way it faces. Some people get hung up on, well, wait, isn't it in the third quadrant, so it should be the other way and down? Yeah, I don't care. Draw the triangle. So, there's the triangle. I'm missing one side. How do I find the hypotenuse? Pythagorean theorem. And in this case, it would be square root of 13. So, if I know that that's the square root of 13, then what's the cosecant of that angle? Cosecant. Cosecant, reciprocal of sine. Sine of that angle is 3 over the square root of 13, therefore the cosecant would be 13 over 3. Shazam. When in doubt, pull a fire alarm.
Yes.
Good. Back in the old days, they used to have fire alarms where you had to stick your hand up in the bottom of it, and like this opening, and when you pulled it, it would clamp onto your wrist, so you'd run around with this big metal thing on your hand. So you knew exactly who pulled it. Now it just sprays dye all over you.
Oh, really?
That little bar that you break? You ever seen fire alarm? You know, it's got a little glass bar in there. When you break that, ink sprays off.
So you just like pull it down.
You do, and it breaks the bar. That's what sets off the alarm. Go try it.
What if it's a...
Well, they just want to know.
Wait, then why do you pull the fire alarm?
To save lives.
Well, there's an
Let them burn, baby. Let them burn.
There's an actual fire inside your hand. Why do you want the sweaters to sign?
It actually does. Really?
Why would I like to? Uh-oh, wait a second. In number 3, we have numerical values. Easy to set up a triangle. In this one, we don't have numerical values. We have an X. What will you do?
Run.
Yeah, we forgot about running. Yes. We could go through that whole process again. However, when in doubt,
Triangle.
Triangle! Woo-hoo! There's the triangle. Remember, x is x over 1.
Dude.
How long is the missing? How long is the missing side? Go, Kaylee.
It's like x squared squared, or squared, x squared root of 2 or x squared 3. Because you know it's like x and then, oh yeah, that's 45.
1 minus x squared.
Because we don't know that it's 45, 45, 9 here, 30, 69. Yeah. Anybody else?
Square root of 1 minus x squared.
Yep.
Sometimes, man.
And so the business inside the parentheses helps us set up our triangle. The stuff on the outside then could be anything. Secant, cosecant, tangent, cotangent, whatever it is. Because now that you have the triangle, you should know each of those functions. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, reciprocals of each one of those respective things, so you can get all 6 of any of those triangles. Dun, dun, whoops, sorry, little itchy trigger finger there. So the cosine would be the adjacent over the hypotenuse is 1, and we're done. Still review, yes? Still review, yes? How do I get rid of the arctan? Take the tangent of both sides. Love it.
Is that the best we've ever finished? I'm just going to keep looking. And then a positive note.
Tangent of pi over 4 is 1. Arctangent, or tangent of the
Oh
arctangent,
yeah.
2x minus 3. Do we need to go through how to solve that linear equation?
Yes.
Okay. Okay. So you would start by multiplying by 2,
What?
then take the square root of both sides, and then add 4 to both sides. And you end up with 2. Lindsay's had enough, she's going to pull the fire alarm. Okay, that's all review, right? Right. Let's talk about derivatives. I could sugarcoat this, but I'm not going to. This is icky. Are you ready?
Yes.
Those
Those are all formulas. Okay.
So here's what we're going to do. I'm going to give you an opportunity to copy that down. You can, if you don't get it, you can go back and see the slideshow later, whatever. Take a picture, I don't care what you want to do. But after that, I'm going to show you where these formulas come from. We're not going to derive all 6 of them, but I'm just going to do one of them. And that way you have an idea of where these come from. Now, why would I bother doing that? I know you don't care about it. However, if on the AP test, all of a sudden you lock up and you can't remember what the derivative of the arc cotangent is, maybe seeing this method will give you a little opportunity to figure out what the formula is.
You too. That's fine.
The most frustrating thing for me in trying to remember these is remembering where minus signs go and that kind of stuff. Notice that all the functions on the right-hand side have minuses in them. The ones that begin with C, you can see that they have a minus sign. I don't know what to tell
Just
you.
like a golf.
Going across, the co-functions are the same except for a minus sign. So sine is the same as cosine, except for the minus sign. Tangent is the same as cotangent, except for the minus sign. Secant is the same as cosecant, except for the minus sign. Okay, we good? I would concur. Let's derive one, just to show you where it comes from. So we'll do an inverse sine. It's easy peasy. So we know that. We're working with the sine, inverse sine function of some value x, and we're calling that function y. Which means that if I take the sine of both sides, I end up with that puppy. The sine of y is equal to x, similar to what we used in solving that tangent equation a couple slides ago. Which means I can draw a triangle. When in doubt, draw a triangle. Whoops. Whoa, 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 whoa. When in doubt, draw a triangle. Got some angle y. When I take the sine of it, I get x, which is x over 1. That triangle looks familiar because we used it in a previous problem. Okay, doke? All right. Now, the fun part. Implicit differentiation. Derivative of sine is cosine. Since you took the derivative with respect to y, you need a dy dx on there, or a y prime if you prefer, and the derivative of x is 1. Okay, so that's the derivative of the sine of y equals x. We good? Yeah. Okay. I'd like to know the derivative, which is the dy over dx, so I would divide both sides by the cosine of y, and I get that. Hold the phone. What's the cosine of y?
Square root of 1 minus x squared.
You bet. From the triangle we have, we know what the cosine of y is. It's the square root of 1 minus x squared, and gives us blammo. There it is. That is the same formula as that, except we stuck u's in instead of just x's. That's where it comes from. And I wouldn't expect you to do this every time. In fact, I wouldn't expect you to do it at all. You're probably just going to put those 6 functions on a flashcard and memorize them. Whatever works for you, I'm okay. Or maybe you put 3 of them on a flashcard with a little note that the c's begin with negative signs. Whatever works best for you. Okay, but every one of those functions can be derived using a similar process. Good? Questions? Hot diggity. Okay, what's u? No. From my head. What's u? 2x. Good.
Super Mario Brothers, that's what it is.
What's u?
3x.
3x. So I'm going to go through these quickly, but basically it's a process of what's u, plug and chug. What's u, plug and chug. So in part A, u is 2x. Go and find the formula, plug and chug. What's the formula? U prime over the square root of 1 minus u squared. Gets a little ugly in C, but still manageable. No fractions within fractions, no negative exponents. I cleaned it up a little bit. Ooh. Let me explain that last step. What the heck did I do? Yeah, I just combined the 2 radicals into 1 radical. X times 1 minus x is x minus x squared. Ooh, now some e comes in there.
Yeah.
I can't do that.
About.
Sorry. What would be worse? We could do kind of an inception thing and do some trig inside a trig. Okay, I won't then. It's fine. I'll just leave it like that. Okay? Ooh, getting all fancies in my panties. Who cares? Okay. Ooh. Notice that e to the 2x is the same thing as e to the x raised to the second power. So it's going to be a positive value, so I don't need the absolute values there. But again, better off to just put them in there and leave them there, even if you think you don't need them, because again, better to have them and not need them than to need them and not have them.
Yeah.
Here it is. This is every differentiation rule we've learned from day one. Oh, there's another slide, by the way. Okay. So number one, constant rule. Derivative of 2x squared is the derivative of x squared times 2. Second one, the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. What's number 3 known as? Product rule. Number 4. Which one? Quotient rule. Number 5? Constant rule. Number 6? Chain rule. Very good. Number 7? Common sense. Great. Number 8? We didn't really do number 8. Okay. How do we talk about doing the derivative of absolute values? Looking at getting either 1 or -1 because it's going to give you a v. And then 9, 10, 11, and 12 we just learned in this chapter. Oh, look at all that stuff. Yeah. Well, not all of them. The bottom 6 are from today. Top 6 are from this chapter, though. We've known 13 and 14 for a while. No, we're not having a quiz tomorrow. When are we having a quiz? So let's suppose there's a pretty good chance that we don't have school tomorrow. Because when you make students stand outside at -40 below, their eyeballs freeze. And then everybody would stare at you all the time like this. And I couldn't handle that. So we probably won't have school tomorrow. There is a pretty good chance that we also won't have school on Thursday. But that's not a definite. You also don't have school Friday because it's TPC day. So there is a possibility, as much as it saddens me, that I will not see you till Monday. I know. And who knows what could happen over the weekend? It could be another polar freeze come in and
It's like,
be like that.
high 30.
Yeah, it's going to rain on Sunday. So that probably won't happen. But anyway, regardless of what day I see you next, whether it's tomorrow or Thursday or Monday or 3 weeks from today, whenever I see you next, we will have the next quiz. Okay?
So Monday?
I'm sorry, what? Okay. Thanks, Ben. Appreciate it. Any questions?
Wait.
Amanda? This is not on the quiz. God had nothing to do with it.